Hello students, today I'm going to do my review for Chapter 5 Stereochemistry that I covered in lecture on Wednesday the 12th. So this is Chapter 5 Stereochemistry, very important topic in organic chemistry. Oops. And again, this covers the lecture, only one lecture from this past Wednesday. Let's see, that would be the 12th, right? 14. Alright, so in Chapter 5, essentially we have a bunch of similar topics that are all very closely related to each other. And so I'm going to list them out very quickly, and we're going to get through most of them in one lecture, actually. So the first one is that of stereoisomers. Stereoisomers. What is a stereoisomer? What is a stereocenter? Okay. Chiral centers. So it's spelled C-H-I-R-A-L, but it's pronounced chiral, like chi. So chiral centers. Some fancy words here: enantiomers, E-N-A-N-T-I-O-M-E-R-S, as well as diastereomers, E-O-M-E-R-S, diastereomers. We also have mesocompounds, which we're not going to talk about in this lecture. I'm going to save that for the next lecture. Mesocompounds. Then we have the RS nomenclature system. And then finally, a little bit of optical activity. Optical activity. And then Fisher projections. Alright, a projection is a way to draw a two-dimensional structure or three-dimensional structure two-dimensionally. Alright, so let's start with stereochemistry. A few definitions. Stereochemistry. Okay. So stereochemistry is simply the study of the 3D structure of molecules. Right? Study of the three-dimensional structure of molecules. Right? We all know, sure, of molecules. We all know molecules are not flat. Right? We draw them flat, but we know they're not really flat. Right? They occupy volumes in space. And so even though it's technically correct to draw methane this way, often we use these dashes and wedges to represent coming out at us and going back away from us. Right? To give us a little bit of three-dimensionality to the structure. Try to give us some perspective. Right? Some molecules have very specific locations in their orientation in space, which are different from a similar but different orientation of space. I know that sounds confusing, so let's take a look. All right, so let's talk about stereoisomers. Stereoisomers. Isomers. Okay. What is a stereoisomer? A stereoisomer is a molecule that has the same bonding sequence, so the order of the bonds is the same. Right? It goes carbon, then hydrogen, etc., etc. But it differs in their orientation in space. So in the case above with methane, it doesn't matter. A hydrogen is the same as a hydrogen is the same as a hydrogen. But if we didn't have hydrogens and we had different groups attached, then we have a different game. So let's think about a simple example, right? We've already seen constitutional isomers, right? Like 2-methylbutane, right? A constitutional isomer of 2-methylbutane would be something like 2,2-dimethylpropane. Something like that, where I chop off this methyl group and I attach it to this carbon. That would give me this molecule. The bonding sequence is different here, right? It goes carbon, 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 and then at the 2 position another carbon. This one goes carbon, 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 and at the 2 position now I have 2 methyls, right? So this is a constitutional isomer of this one, even though both of them are, what, C5, H, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, H12, right? They're both C5, H12. They're different conformational isomers of C5H12. Okay, but if I had different orientations in space, then I would have stereoisomers. Okay, so I'll get there in a second, but let's talk about enantiomers. And in order to understand enantiomers, first we have to understand chiral centers, which is a fancy way to say what we're about to address. Okay, so a chiral center is an atom that has handedness. All right, so what the heck is handedness, right? What does that mean? Let's take a look. As handedness, right? Your handedness. I'll put that in quotations because I think I might have made that word up. All right, so think about it this way, right? Look at your left hand right now. If you look at your left hand and you hold it out in front of you, so your palm is facing down, what do you see? You see something like this, right? Finger, 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 thumb, right? Maybe your hand's a little prettier than that. If I hold up my right hand, what would I see? I would see, if I hold it up palm down the same way, I'd see thumb, and then finger, 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 finger. Maybe it doesn't look like a claw, etc. Something like that. Try that again. Finger, finger, finger. Doesn't matter, whatever. Two hands, right? No matter what I do, right, I can never take one hand and superimpose it, meaning put it in the same exact orientation and location space as my other hand, right? Another way to think about it is if you look at your left hand, right, so this will be your left hand, this will be your right hand, and you hold up your left hand to a mirror, okay? So if you go in your bathroom right now or you go in your bedroom and you hold up the mirror and you look into the mirror, what are you actually seeing in the mirror? You're actually seeing your right hand. Right? That matters. And that's very different for things that have handedness or things that have chirality. Think about a chair, right? I'll draw a picture of a chair. Now, okay, so we have, the chair has a back to it, right? And you need to be able to sit somewhere. And it has four legs, 1, 2, 3, 4, right? And if I take that chair and I put it in the mirror, what do I see? Well, I see something that looks kind of like this. It looks like that. And then it looks like that, right? So this would be a mirror image of the chair. If I take this chair and I imagine yanking it out of the mirror, I can superimpose it and place it exactly on top of this chair. Essentially, I can just rotate it about, 20 or 30 degrees in space, such that the image I would get, I'll draw it in a dotted line, right? Right, would look like this. The chair can be directly superimposed atop of the other chair, and every leg would go in the same spot, every back would go in the same spot, every seat would go in the same spot. The chair is completely superimposable. So what we would say then is that the chair does not have this handedness. It doesn't matter if you look at the mirror image of the chair or the chair itself, you're looking at the same thing. That is not the case when you have a hand. When you're looking at your left hand, it's very different than when you look into the mirror and see the mirror image of it. You're then looking at your right hand. You're no longer looking at your left hand. That is what I mean when I say handedness. And the way that we use that word in chemistry is to use the word chiral. Chiral means handedness, right? So to put some real molecular perspective on it, a simple way to recognize a chiral center is to just have a carbon that has 4 different groups attached to it. So for example, if I had carbon with chlorine and bromine and what I use in class, fluorine and hydrogen, right? A carbon that is sp3 hybridized, right? So it has 4 single bonds. And it has 4 unique groups attached. A chlorine is not the same as bromine, not the same as fluorine, not the same as hydrogen. Therefore, we would say this carbon in the center is indeed a chiral center, and the way we usually denote that is with a little star or an asterisk. Okay. This would be very different from the mirror image. If I draw the mirror image, what would I see? Well, I see bromine up close. I see chlorine up on top. But now, pointing this direction, towards us and to our right would be the fluorine, and then back and away would be the hydrogen. If I take this molecule out of the mirror and I rotate the carbon-chlorine bond so that the bromine will now be in our bottom right-hand position, right? So I'm going to say 120-degree rotation. So bromine's going to go where fluorine is going to go where hydrogen is, and hydrogen is going to go where bromine is, right? So 120-degree rotation. If you don't believe me, you should make your model kit and do this. Chlorine ends up being in the same spot. Carbon ends up being in the same spot. But now, if we put bromine here, so we have this orientation of our bonds, hydrogen now ends up here, and fluorine ends up back here. So these two are now mismatched, whereas chlorine, carbon, and bromine are perfectly aligned. I could take those three and superimpose them, but these two are necessarily mismatched. Therefore, we know that these two mirror images of each other are non-superimposable because they have this chiral center. And what we say a molecule that is a non-superimposable mirror image, right? This thing on the left, whatever it's called, is distinct from this thing on the right. How is it distinct? Well, it's still bromochlorofluorocarbon, right? Bromochlorofluorocarbon, still the same. It's just how the atoms are oriented in space is different. So they are stereoisomers of each other. Specifically, they are enantiomers. Enantiomers, by definition, are non-superimposable mirror images, such as this case here. Let's look at some others. If I give you, let's see, butanol, CH3, 2-butanol, CH2, carbon, methyl group, hydrogen, OH, right? There's two ways I can give you 2-butanol. I could say this is 2-butanol, right? So at the 2 position we have an alcohol, so the suffix OL. We'll learn that in chapter 10, so don't worry about not knowing it now. No big deal, right? Say if I say 2-butanol, you could draw this, completely fair, but you could also draw this, CH3, CH2, C. And what I'm going to do is I'm going to keep the OH the same. I'm going to keep the dash and the wedge in the same spot, but I'm going to flip the groups. So the CH3 and the H have now been swapped. This is also 2-butanol. So now we have a problem, right? Because the whole point of having a naming system, IUPAC, is to say, if I give you a name, you give me the structure, there can be only one. If I give you a structure, you give me the name, there can be only one. No ambiguity. If I just say 2-butanol, now it's ambiguous about which stereoisomer, specifically, which enantiomer I'm talking about, because this is the chiral center, right? It's a carbon that is sp3 hybridized, meaning 4 single bonds, and has 4 different groups attached: an OH group, an ethyl group, a methyl group, and a hydrogen. So what we need then is a system to come up with a way to say, okay, this is 2-butanol, this stereoisomer, and this is 2-butanol, the other stereoisomer. And we have a system for that, and we're going to get to it in just a second, but I want to do a few more examples first. Right, so identify the chiral centers. I'll give you a few molecules. I want you to pause the video, and then you just draw little stars on your paper or in your mind or wherever where you see chiral centers. So I'll give you 3 examples. After I'm done drawing these 3 examples, go ahead and pause the video and tell me where the chiral centers are. All right, go ahead and pause it. All right, so hopefully you've unpaused the video now. Now all you need to do is identify all the sp3 hybridized carbons that have 4 different groups attached. First one, this carbon has 3 hydrogens, so that is not chiral. This one has an iodine, a hydrogen, a methyl, and then some other stuff. Therefore, that's a chiral center. This carbon right here has 2 hydrogens on it. That's called a methylene, by the way, a CH2 group. That's like part of a chain or something. That's called methylene versus methyl, which is just this. Right, so methylene groups are always, by definition, not chiral because they necessarily have 2 hydrogens. Since hydrogens are the same as each other, it cannot be a chiral center. Go about here. Methylene, methylene, methylene. Those are not subject to chirality. This one has an OH group, a hydrogen, a methylene that goes to a carbon that has a methyl. This one has a methylene that goes to another methylene. So this kind of side of this chiral center is different than this side, right? The things I circled are different, one of which has an extra methyl group than the other one. And so this guy is indeed a chiral center, and hopefully you were attentive enough to notice that this one is also a chiral center. Notice I didn't draw it with dashes and wedges this time, right? That's not what dictates chirality. What dictates chirality is if you have sp3 hybridized carbon with 4 different groups attached. Methyl, methylene that goes to a carbon that has an OH, hydrogen that's not drawn, and a methylene that goes to another methylene. So that's different. So we have two chiral centers in this one. Same argument here. We have two chiral centers for the same reasons. One there and one here because bromine is not the same as methyl, which is not the same as methylene, 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 compared to methylene and then tertiary carbon. So those are our chiral centers. So now that we know we can identify the centers, now we have to say, well, what about this problem from before, Jay? I really want to know how to name this. And I was like, well, don't worry, you know, we're gonna name stuff because we love naming stuff. The way that we name molecules, stereoisomers, especially enantiomers and diastereomers, is to use a system called the Kahn, Ingold, Prelog. Those are three chemists from back in the day. I don't exactly remember when. System. It's also called the RS system by lazy people like myself. I did not do that. What the heck? By lazy people like myself because Kahn, Ingold, Prelog that's a lot of letters. RS is 2. That's easy for me. So anyway, we have a systematic set of rules that we're going to apply, just like when we name alkanes, just like when we name alkyl halides. We just apply these rules in a systematic fashion, and we necessarily get the correct logical output. Yay, logic. First thing we need to do when applying our system, identify if the system needs to be used in the first place. So identify all chiral centers. And my advice to you is to, once identified, immediately label them with a little asterisk or star. Right? So always tack that on so you know what you're talking about. Step 2, assign priority to the groups that are attached to the substituents. Okay, we'll talk about how to do that in a second. Okay, the easiest way to determine priority is the largest atomic number. Largest atomic number. This supposed to be an A, by the way. Largest atomic. Seriously? Atomic, yeah. Okay. What if there's a tie, right? Like what happens if you have two atoms are tied for each other, like carbon versus carbon? Then we have rule 2A. 2A is if tied, go now one atom out. Not away, out. I'm going to specify the difference from that in a minute, but it's very important that you go out, not away. Okay. 3, after you've done that, assign the priorities, then you need to rotate the molecule. So rotate molecule. Oops, I don't need a comma there. I'm a comma whore. Such that the carbon to lowest priority group. Right, so carbon to group number 4 is pointed away from you. So if you remember, away from observer. So if you remember when we did the Newman projections, right, we would intentionally move the molecule around a little bit, so we'd be looking down the carbon 1, carbon 2 bond, or carbon 3, carbon 4 bond, and then we would say, what would the Newman projection look like if I was looking at the molecule from this point of view? You're going to do the same thing. Okay, and I'll show how to do that. And then the last one, after you've done that, then you're just going to connect the numbers. Connect numbers in order. 1, 2, 3, and then after 3 go back to 1. Okay. If you're going clockwise when you connect those numbers, good old clockwise will give you the R form. If you're going counterclockwise, which is the only other option, then that will give you what we call the S form, and hence the name the RS system. So every chiral center that we generate will always have either an R form or its mirror image, the S form. Of course, let us practice. Let's redo our example from before, 2-butanol. So there's one version of 2-butanol, and I'll draw his mirror image. Did I draw that right? I think I did. Okay. Okay, so there's his mirror image. Let's name this one using our RS nomenclature system, and then to prove that I'm not lying to you, we'll also name this one. Alright, so the first thing we have to do is identify chiral center. So we're looking for sp3 hybridized carbons that have 4 unique groups attached. Well, methyl is different than hydrogen, is different than OH, is different than ethyl. Therefore, there's our chiral center. Label it. Okay. Step 2. Assign a priority to each substituent. Largest atomic number is the highest priority. Well, we have carbon versus oxygen versus hydrogen. Oxygen's atomic mass is 16, atomic number is 8, and so this will be highest priority. Oops, 1 not plus. So I just put a 1 and circle it. Hydrogen is always the lowest because nothing can be less than hydrogen. So hydrogen, whenever you have it, is always number 4. Now rule 2a comes into effect because we say attached to this carbon right here, my chiral center, I have a carbon and I also have another carbon. Now I have a tie, so I go to rule 2a. In case of a tie, go 1 atom out. What does that mean? It says you take the atom that you were talking about, the one that's tied, so you take this one here and this one here, and you say, what is this guy attached to? Well, he's attached to a hydrogen, and then another carbon. So I write that down. Carbon, hydrogen, hydrogen. The order doesn't matter. This guy is attached, because he's a methyl group, to 3 hydrogens. So hydrogen, hydrogen, hydrogen. Write that down. Please write this down. Do not just say, I'll remember, because yeah, sure, you'll remember for one case, but wait till I throw you a diastereomer with 14 chiral centers. Good luck remembering. So write it down. Okay, so 2 hydrogens cancels with 2 hydrogens. Now the comparison says, does carbon beat hydrogen? Who has a larger atomic number? Carbon does. And so this group then, everything attached to it, will be the highest ranking of those 2 options, which makes this one 2, which makes this one 3. Okay. So now I need to orient the molecule such that I'm going to erase this just so I have room to draw. Okay. So now I need to look down the carbon to lowest priority group bond. Well, the lowest priority group is 4, and it's kind of pointing into the page. So I'm already kind of looking at it the right way, from the front of the page down onto the page. So I go from 1 to 2, 2 to 3, 3 to 1. Oops, sorry, 3 to 1. What way am I going? I'm going clockwise, so this is R2 butanol. Okay. To prove it, let's make sure that its mirror image is indeed S2 butanol. Well, obviously this will still be 1, this will still be 4, not 2, it'll be 4. The ethyl group will be 2, and the methyl group will be 3. So I go 1 to 2, 2 to 3, 3 to 1. Which way am I going? I'm going left or counterclockwise. So this is S2 butanol. And so this is how we name molecules that contain chiral centers. Every time you have a chiral center, you have to give it a corresponding R or S nomenclature. So let's see, let's do some more examples. Let's go over here and we'll draw CH3, CH2, C. And after I'm done drawing this, go ahead and pause the video. See if you can come up with the name. It is just an alkyl halide. And don't forget to include the chiral center. Go ahead and pause the video now. Alright, let's see what you got. There's our chiral center. Those methyl is different from ethyl, is different from iodo, is different from hydrogen. The highest priority group clearly would be iodine. The lowest priority clearly would be hydrogen. It's always the case. Who wins, methyl versus ethyl? Well, because the argument we just made over here, ethyl will win, so he will be 2. He will be 3. Conveniently, I've drawn it so the hydrogen is already pointing away from us. So I just have to go 1 to 2, 2 to 3, 3 to 1. Which way am I going? I'm going counterclockwise. So this will be S at the 1, 2 position now. I'm counting the chain. Okay, so I'm done with the S, so I can erase all my stuff. I'm done with the chiral center stuff. Now I'm just doing normal nomenclature stuff. I count carbons 1, 2, 3, 4. Puts the substituent at the lowest possible number, 2. So S2 iodo. And how many carbons are there total? 4, so that's bute. And it's an alkyl halide, or it's an alkane, because it only has carbons, hydrogens, and then the halogen. So it'll be butane. So the name of this molecule will be S2 iodobutane. Okay, let's do another one. Let's do this one. I like this one. Okay, H3C, C, C. And this time you don't have to give me the full name because we obviously didn't name thiols yet, but I do want you to give me the RS-ness of all chiral centers. Oops, this should be like that. Okay. Go ahead and pause the video and solve the chiral centers and determine R or S. Alright, let's see what you got. We have a carbon, sp3 hybridized, 1, 2, 3, 4 different groups attached, so that's chiral center. Carbon here, which, oops, I'm sorry, I forgot to give you a methyl group. Makes the problem a little difficult when you don't have the complete problem. So, 4 different groups attached. Even if you assumed it to be a hydrogen, it would still be a chiral center, but I specifically want this one to be methyl, no big deal. So, SH versus methyl versus isopropyl versus some other stuff. 4 different groups, therefore chiral. So let's name this carbon first. Okay. What is the highest priority group that we have? We have C versus H versus O. So O wins, H loses. Then we have carbon versus carbon. That's a tie, so we go one atom out per rule 2A. Hydrogen, hydrogen, hydrogen versus sulfur, carbon, carbon. And it's very easy distinction. This one wins. So 2 and 3. Hydrogen is already pointing away from us, so we go 1 to 2, 2 to 3, 3 to 1. So I'm going S. So that this carbon here is S configuration. I can do the same type of analysis for the other chiral center, and I will as soon as I erase the rest of my junk. Okay. Highest priority group. We have carbon versus sulfur versus carbon. Who wins? You betcha. Carbon wins. Now we have a three-way tie. Carbon versus carbon versus carbon. That's okay. You can have three-way ties. You go one atom out. So you say, this atom, what is he attached to? A hydrogen. That would be this one. A carbon here and a carbon there. So HCC. What is this guy attached to? 3 hydrogens. HHH. And what is this guy attached to? A carbon, hydrogen, and oxygen. So carbon, hydrogen, and oxygen. Hydrogen cancels hydrogen, cancels hydrogen. This one only has 2 hydrogens, so clearly he will be the loser. So he will be our 4. Now we have carbon cancels carbon, and now oxygen versus carbon. Who wins? Oxygen wins, so he becomes 2. He becomes 3. Just to clean up my drawing, I'm going to erase what I just wrote, just so we can see it a little bit better. So now we go, the lowest priority group is pointed away from us, conveniently. You're welcome. 1, 2, 2, 3, 3, 1. Which way am I going? I'm going to the right, so this is R. So we would say that this one is S and this one is R, right? And if we were going to name it, we could name it if we wanted to, but we don't know how to name thiols and alcohols yet, so I'll just skip over that for now. We'll come back to that when we get to chapter 10 or 12 or whatever it is. All right, let's do one more, and then we'll actually come up with the full name, and then the full name, and then we'll move on. All right, pause the video, tell me the name. Hopefully you've unpaused the video and you've identified that this is a chiral center and that this is a chiral center, right? These are all methylene groups, so by definition they cannot be chiral centers. We say, okay, chlorine will be the highest priority, which means I have a hydrogen that isn't drawn. Here I have hydrogen that isn't drawn, and it's a wedge because this chlorine's a dash. So that's 1, this is 4. I have carbon versus carbon, that's a tie. Per rule 2A, I go one atom out, so I go chlorine, hydrogen, carbon. Chlorine, hydrogen, carbon. Here I go hydrogen, hydrogen, carbon. Hydrogen, hydrogen, carbon. Doesn't take long to notice chlorine kills hydrogen, and so this will be 2, and this one will be 3. Okay, so I go, the lowest priority group is already pointing away from us. Yay, convenient again. 1 to 2, 2 to 3, 3 to 1. Which way am I going? I'm going counterclockwise, so that is S. That takes care of the lower chiral center. Now we need to do the upper chiral center, and I'm going to show you a shortcut. So chlorine again is 1, hydrogen again is 4. Using the same argument, this one will be 2, and this one will be 3. Now, if you notice, the lowest priority group is pointing at us, right? It's a wedge. So one of the things you can do as a trick is, in the event that the lowest priority group points at you, because sometimes it's easier to draw, or in this case it's already drawn for you, what you can do is follow all the rules the exact same, do everything we just did, 1 to 2, 2 to 3, 3 to 1. So if the lowest priority group is pointing away from us, we would get R, but because it's pointing at us, we flip the answer. We get S. So because we flipped the lowest priority group's orientation in space towards us versus away from us, the answer that we get in the very end is going to be the opposite of the one we get when we follow the rules. So we get SS. So how do I name this? Well, I say now I just go back to naming my normal, oops, I don't know how to undo, so I'm going to redraw it. I just go back and I name my molecules, my alkyl halides, the same way that I normally do. I say, okay, one of these is carbon 1, this will be carbon 2, 3, 4, 5, 6. So it'll be a cyclohexane. And at the 1 position I have a chloro, and at the 2 position I have a chloro, so that's going to be a dichloro. Okay. And I have to specify their stereochemistry, so I say at the 1 position it's an S, and at the 2 position it's an S. So 1S, 2S, dichlorocyclohexane. Right? In this specific case, I could have also said trans dichlorocyclohexane, but 1S, 2S is a better way to name it because there's zero ambiguity. Trans means it could be this way, or it could be this way, right? So technically there's 2 different names if you just say trans 1,2-dichloro, right? Because this is not the same as that. If you try and flip it over, they don't superimpose anymore. So anyway, that's how we use the RNS system. Everything that I talked up till this point you should be able to use to do Chapter 5 homework, with the exception of the next 2 categories I'm going to talk about, which is that of diastereomers and meso compounds. So I'm going to stop and I'm not going to talk about meso compounds, but I just want to give you a quick note about why this stuff is important, right? If anyone ever has headaches and they take naproxen, which is, naproxen is not Advil, it's Aleve. That's my favorite one, Aleve, right? Naproxen looks like this, right? Naproxen is this molecule, but specifically it's this, right? This is S-naproxen, which cures your headaches. If by some random chance the chemical that they put in the bottle is this, because the organic chemist who made it is not good at stereochemistry and gives you by accident R-naproxen, this is a fatal liver toxin and will kill you. So, you know, stereochemistry matters, right? And there's tons of examples if you look online for different chiral centers that will kill the game. I'll give you one more example just because I think they're cool, right? So we got, I'm not going to test you on this type of stuff. It's kind of FYI, like, hey, look, this is interesting, and it does matter. It's not just completely abstract nonsense. Okay. Right? So we have a chiral center right there, right? This is, this is Lunesta, right? It's a sleep agent. If you have different chiral center, it's a brain toxin. You don't want to take that, right? And then there's a whole bunch of them I can give you, but you can look at them yourself. I don't want to go into it right now. Okay, so that's RNS, that's enantiomers, right? If the R form. So an easy way to tell if you have an enantiomer is very easy. You name it, you come up with an RNS. That means it has a non-superimposable mirror image. So one form would be S. The enantiomer would necessarily be R, right? So you take all the S's and convert them to R's, all the R's and convert them to S's, right? So in the case where we have multiple stereocenters, it matters a lot. Okay, so what happens if you don't take all the S's and all the R's and flip the chiral centers? What if you only flip some of them? All right, so for example, let's give you this molecule, Cl. We'll just stick with the alkyl halides because it's nice and easy. All right, and I say, well, let's compare that to this molecule. It's very easy just to look at it and say, well, yeah, they're different. These this molecule has 2 chlorines that kind of point at us. This molecule has 2 chlorines that one that points away, one that points towards us. The stereochemistry of this carbon is the same in both cases. So I'm not going to name it right now, but if you pause the video and name it, you'll find out this carbon, if I go 1, 2, 3, 4, 5, right, is 2R, 4S. So the stereochemistry of position 2 has not changed. So this one will be 2R. But because the stereochemistry of carbon 4 has been flipped, where the chlorine has gone from a dash to a wedge, now it won't be 4S anymore. It'll be 4R. So 2R, 4S, 2R, 4S dichloropentane, 2R, 4R dichloropentane. Right? But what is the relationship between these two molecules? Well, the relationship is not that of enantiomers anymore, because enantiomers, by definition, are non-superimposable mirror images. This is not a non-superimposable mirror image of this, because one points towards, one points away. The mirror image would be both of them pointing away, right? Which is actually the same thing, because you can spin it around and superimpose it then. So we have a word for that. We'll talk about that next time. So the relationship between these two is one of diastereomers. Okay, so a diastereomer is when some R's go to S's, or when some S's go to R's. Right? The requirement to have diastereomers is at least 2 chiral centers. If you only have one chiral center, it can only be R and S. So if you have R, the only thing you can do is flip it to get S, and then you necessarily have enantiomers. So if you have more than one chiral center, then if you flip some of the chiral centers, in this case carbon 4, but you don't flip all of them, such as carbon 2, then you'll be generating diastereomers of each other. And so the very common question is, I'll give you a molecule, and I'll say, or excuse me, I'll give you 2 molecules, and I'll say, what is the relationship between these 2 molecules? Right, let me try and find the exact example I used in class. Here we go. So on the test, I might say, here's a molecule, and so let me finish drawing. And of course, I'm going to draw it in a very convoluted and confusing manner because, you know, it's a test, it's my job. So I'll say, here's another molecule. What is the relationship between these 2 molecules? Are they enantiomers? Are they diastereomers? Are they constitutional isomers? Are they... come on, pen, being stupid. Are they the same compound? Are they completely different compounds? Right? There are a couple different ways you can do this. You can waste lots of time by building each model every single time and then trying to put them on top of each other. That is a terrible way to do it, but it's technically possible. You can look at it and manipulate them in your brain and say, okay, if I rotate this 120 degrees, I spin this bond, I flip the whole thing 180, and I try to superimpose it, what do I get? Eventually, you might be able to do that. I can do that, but it's not very easy, right? It takes a lot of practice. In my opinion, the easiest way is to just name the molecule. If the name matches every single part, including the chiral centers, then it's the same compound. If the name matches, but the chiral centers don't match, then you can use the information as to what does or does not match to determine the relationship. Let me explain what I'm talking about. So we have a 4-carbon chain here. 1, 2, 3, 4. And here we have a 4-carbon chain. 1, 2, 3, 4. Okay. So identify the chiral centers. 1, 2, 1, 2. And I say, okay, I'm going to name this molecule, then I'm going to name this, and I'm going to compare the 2 names. Okay, so I have a hydrogen that's pointing away from us. That's good. So bromine will be 1, hydrogen will be 4. A carbon with stuff is going to be 2, and carbon with no stuff, i.e. methyl, will be 3. So the top carbon, the one with the bromo, will be 1, 2, 3, will be R. So that's going to give me 2R, assuming that this is carbon 1, 2, 3, and 4. Okay, I do the bottom one. I do the same argument. I'm going to go a little quick here because you can do this on your own. Right, so there's my chiral center, hydrogen, lowest priority groups pointing away from us. So I have chlorine is 1, multiple stuff group is 2, methyl is 3, hydrogen is 4, 1, 2, 3, 1, 2, 3. That gives me R. So that's 2R, 3R. And then 2R, 3R, 2-bromo, 3-chlorobutane, if I wanted to actually give the rest of the name. I'm not interested in that. I'm just interested in the stereochemistry right now. So same thing over here. I say, okay, bromine is number 1. The carbon with the rest of stuff would be number 2. Hydrogen is always 4. Methyl group would be 3. Hydrogen in the lowest priority groups pointing away. So 1, 2, 3, 1, 2, 3. So carbon number 2 in my nomenclature system, which is the one that bears the bromine, carbon number 2 has a stereochemistry of S. So it's 2S. And then I do the same argument for the lower chiral center. Say, okay, hydrogen is 4, chlorine is 1, carbon with stuff will be 2, methyl will be 3. Now the lowest priority group is pointing at me, so instead of trying to redraw the molecule, I can just say, oh, I'll use the shortcut. 1, 2, 3, 1, 2, 3. That would be R, but because the lowest priority group is pointing at me, it becomes S. So I get 2S, 3S, 2 bromo, 3 chloro, butane. Now I say, what happens to all the R's? Well, all the R's have turned into all the S's, and so the relationship between these two molecules is that of enantiomers. So we'd say each compound is an enantiomer of the other, using it as a noun, or you can say the relationship is enantiomeric, using it as an adjective, right? It describes the relationship, but it also describes the identity, and that's also very confusing. Okay, so those would be enantiomers. So do the homework and try and determine which ones are enantiomers, which ones are diastereomers, etc., and you'll see what I'm talking about. So that's about where I got to last time. There's one more thing that I'm going to mention next week's lecture on Wednesday, because we don't have class on Monday, and that's that of mesocompounds. So the mesocompounds are kind of like a special class of stereoisomers. If you remember a couple weeks ago, I had you draw a chart in your notebook, and I said we're going to come back to it, and it looks something like this. I said we have compounds with the same molecular formula, right? And I said it can be two ways, so you have to kind of go back in your notes. Is it different connectivity? If the answer is yes, then they are constitutional isomers. Right? So I took the methyl group off and I stuck it somewhere else. I chopped off my arm and connected it to my leg. I took the steering wheel off the car and connected it to the roof. Right? I did something like that. If the connectivity is the same, right, that's what we've been talking about today, then we have a couple different choices. We can have things about rotation, about a single bond, a single sigma bond specifically, right? The relationship between those molecules then will be one of conformational isomers, right, which are called conformers. Okay. If it's not rotation about a single bond, then you have stereoisomers, and that's what Chapter 5 is about, stereoisomerism. Okay. With stereoisomers, how many chiral centers do you have? The number of stereocenters. And stereocenter is not the exact same thing as a chiral center, but the distinction is very small. So I'm just gonna for now equate them, but technically they're not. If you only have one stereocenter, right? So if you only have one, the only thing you can have is enantiomers. You can have the R form, you can have the S form. That's it. If your number of stereocenters is greater than 1, then you can have a couple different options. If some of the centers are reversed, right, so some of the R's goes to S, or some of the S's goes to R, some centers reversed, then you get diastereomers, like I mentioned above. Stereomers, okay? If all of the centers reversed, then you have two possibilities as well. If you reverse all the centers and they're non-superimposable, you get enantiomers. Just like this example, right? All R's have gone to S. There's more than one chiral center, and so these are non-superimposable mirror images, and so they are enantiomers. And then that's where we stop today. And the last is, if you reverse them all and they become superimposable, then you're in a special class, a special category. Those are called mesocompounds. And so we'll talk about that next time. So that's where I'm going to leave off. Go ahead and do Chapter 5 homework. It is due Wednesday, this upcoming Wednesday, which is the 19th, because we do not have class Monday the 17th due to President's Day. Yay, Abraham Lincoln. So you should be able to do all of the homework from Chapter 5 with the exception of a few of the ones that involve meso compounds. So if you come across that, just go ahead and just skip it and we'll come back to it. But have a good weekend, and I'll see you guys next week.